Hello everyone, and welcome back to another of our openEuler mini courses. I'm Doria from the G11N SIG of the openEuler community, and in this episode, I'm going to talk about the User Space Accelerator Development Kit, or UADK, a set of hardware accelerator development tools. This kit is designed for user applications to access hardware accelerators in a unified, secure, and efficient way. Before we jump in, let's ask a question. What is a hardware accelerator? Well, hardware accelerators, also called co-processors, are hardware components that work with processors to make certain tasks faster. Because general-purpose processors are designed for a wide variety of workloads, their processor architectures may not meet the requirements for specific functions or workloads. In this case, we can use both processors and hardware accelerators to bring the advantages of programmability for the software stack running on a processor, while delivering better performance for functions running on a purpose-built hardware accelerator. So, what's the relationship between UADK and hardware accelerator? As the name indicates, UADK is a User Space Accelerator Development Kit. The technical foundation of UADK is a Shared Virtual Addressing (SVA) or Shared Virtual Memory (SVM) technology that allows sharing virtual address space between accelerators and processors. SVA works by creating a unified address space that allows multiple devices or applications to access the same physical memory. Because of the unified address space, hardware and user space processors can share the same virtual address in the communication, thus simplifying the I/O memory management for device drivers and user space processes. You can find more information about SVA in our previous mini courses episodes. Based on SVA, UADK provides a unified programming interface that leverages hardware accelerators, freeing up CPU computing power for better performance. It comprises kernel space UACCE, user space libwd, and algorithm libraries for different applications. First, let's take a look at UACCE, a unified accelerator framework. It works to ensure compatibility of mainstream SVA-based hardware accelerators with UADK. UACCE targets to provide shared virtual addressing between accelerators and processors, so that an accelerator can access any data structure of the CPU. This differs from data sharing between the CPU and I/O devices, where only the content of data, but not the address, is shared. UACCE takes charge of address sharing by using a system called mmap and IOMMU, the Input-Output Memory Management Unit. Hardware accelerators are registered as different character devices to UACCE by using vendors' kernel space drivers, in which users can simply perform user space operations on the character devices for quick access to the hardware accelerators. The next component is libwd. This is the UADK fundamental library that wraps basic operations to UACCE devices. It contains a set of helper functions. These helper functions act as an interface for vendor drivers to access memory through UADK. libwd is only accessed by vendor drivers. The last core component is the algorithm layer. It consists of multiple algorithm libraries that offer a set of APIs, through which users can execute specific tasks without accessing low-level algorithm implementations. For example, libwd-comp can be run for compression and decompression, and libwd-crypto for encryption and decryption. Currently, UADK supports 3 types of algorithms as shown on the screen. Here comes the UADK architecture. This diagram shows how UADK works. UACCE provides a unified channel between the kernel space and the user space, allowing user applications to access the hardware accelerators. Hardware accelerators are registered as character devices to UACCE by using vendors' kernel space drivers, and hardware information is exposed to sysfs. In the user space, libwd works with user space drivers to let upper user algorithms directly access hardware accelerators through the user space drivers. Using UADK has a whole host of benefits. First, UADK provides a unified channel. Based on SVA, UADK enables hardware accelerators to share unified CPU page tables. Second, UADK improves efficiency. Devices can directly initiate direct memory addressing DMA operations based on virtual addresses requested by user space processes, avoiding system calls and cross-layer memory copy, and slashing the time for address conversion. And last but not least, UADK ensures security. Based on the IOMMU, the access permission for devices and processes is restricted. With these benefits, UADK can supplement operations in big data, data confidentiality, intelligent security, web services, and distributed storage. If you are interested in UADK, you can try it now. In the following slides, I will introduce 3 methods for installing UADK. The following prerequisites are needed to prepare your environment. Your hardware accelerator must support SVA. The OS must support IOMMU and SVA, and the Linux kernel must support UACCE. Ensure this by upgrading the kernel version to 5.9, at least with SVA enabled. With the requirements met, you can continue to install UADK. The UADK algorithm library can be installed using the YARM source or RPM package, or built from source. To install it from the YARM source, run the YARM install libwd command on openEuler 22.03 or later. To install the RPM package, go to the openEuler community via this link. After obtaining the package, run these commands to install it. You can also build UADK from source code. You can obtain the UADK source code from the Linaro community via this link. Then build the source code following the instructions on this page. On the openEuler website, you can find the UADK Quick Start Guide to help you load the UACCE driver, UACCE KO file, and accelerator drivers. Then, you can start your journey with UADK. Currently, the kernel of openEuler 21.09 supports UACCE, and the UADK library libwd 2.3.11 is available in the openEuler community. Moreover, Kunpeng hardware accelerators have been registered with UACCE. Through the UADK Framework, you can run cryptography and compression algorithms using the hardware accelerators instead of CPU, freeing up CPU computing power and improving computing performance. We have now reached the end of this course. In this video, I introduce a user space accelerator development kit, its key components, architecture, and technologies on which it relies, which are SVA and IOMMU. If you are interested in Linux kernel or openEuler, visit our SIG page and stay tuned for more mini courses. Thanks for watching and see you next time.